Hello, everyone. I'm glad you're here. I hope you had a good lunch. We're going to talk about IPv6 today. We're going to discuss a protocol, a subprotocol in the IPv6 stack. It's called MLD. And as you see, the title of the talk is MLD Considered Harmful. As we've spotted on the tests and on the analysis we did of the protocol and some tests we did with some devices, some of which you see here, we've come to the conclusion that MLD isn't needed most of the time, and it's not something you necessarily want to have in your network. So in order to understand a bit why we came to that conclusion and what the statement actually is, Rafael is going to tell you a little bit about the protocol, a little bit about the how the protocol works, how the queries, the reports. You're going to learn a bit about IPv6 and learn a bit about the protocol itself. And then we're going to come to some tests which are going to show you what MLD can do if not used appropriately. So yeah. So my name is Jason Salazar. I come from ERNW. My colleague is Rafael Schaefer. He also comes from ERNW. We're a penetration testing company with headquarters in Heidelberg, Germany. And what we do is mostly infrastructure, network penetration testing, web application pen testing, everything what is related to pen testing. And with us today should be Antonius Atlasis. Sadly, he couldn't make it to Singapore, but kudos to him. We hope he's doing all right. And without further ado, let's just get started.
So, okay, let's start with some background information about IPv6 and MLD. And first of all, let's take a quick look at the web content available over IPv6. We see a strong growth in this, and more than the half of the world is mostly available over IPv6, at least the web content. And as we take a little look at the user amount, this is not that big as the web content, but statically growing, at least in Europe and America, but in Asia as well. So the IPv6 vision, the Internet of Things, everything is connected, your TV, your fridge, your phone, your watch, everything wants to connect with the Internet, and this will all rely on IPv6. So even your research or monitoring will rely on IPv6 or some sensor networks, and IPv6 is coming, and we should take a closer look at this. This sounds all great, that we can connect everything, and but how good is our knowledge about IPv6, or is your knowledge about IPv6? And we saw some package in our infrastructure, like you can see here, and we wondered, what are these about and what is behind this protocol we are seeing here? And this is where we basically started the whole research, and the protocol was MLD, Multicast Listener Discovery Protocol, and it's an essential part of IPv6, and its purpose is for discovering and managing multicast groups in your network. But let's start with at the beginin. So the unicast way is we have a one-to-one communication. This is for like a TV show you're broadcasting in your network, not as good, since every receiver has to connect to your sender, and every packet, even if it's similar to you, to all the other senders, you send at least as most as receivers you have. So the multicast way is you have one sender which sends its data stream in the network infrastructure to a called multicast group, and everybody who wants to join this group to watch like a TV show which is presented over there, can join this group, and the network infrastructure will manage to duplicate the stream and to get the information and the data stream to the listeners. But how does the infrastructure manage all these kinds? So, but before we coming to this, where is multicast being used? I mentioned it already. IPTV is a big thing where multicast is playing a big role. Video conferencing as well. Sensor networking or auto configuration and monitoring in your environment is also a possible scenario for multicast. And since in IPv6 there is no broadcast anymore, it is replaced by multicast. Even there is a multicast group which is similar to a broadcast, but everything is handled with broadcast. And even the initial neighbor discovery and solicit node discovery is managed over multicast addresses. And for these purposes, we have this multicast listener discovery protocol to manage all kind of multicast traffic in IPv6 in the local link. So MLD should make our life much easier, or at least if we understand how MLD works. Our initial scenario is we have our data streams or our multicast sender in our environment, which sends this data stream to our network infrastructure, and then we have some listeners who want to get in contact with the stream or get the data from this stream, and they will call our router and say, hey, I would like to listen to this multicast group, they have some data from me, and then the router will take action to get the data stream to the listener. And this initial communication with the router is managed over MLD. This all started back in 1999 with MLD version 1. Since now this is superseded by MLD version 2 in 2004. But MLD version 2 is still backwards compatible to MLD version 1. So basic MLD operation is we have our router, which is called the querier, and he will announce, hey, if there's any listener in my network infrastructure, please contact me and tell me which multicast group you want to join. And our listener will then send back a report and let the querier know, hi, I would like to listen to these multicast groups. Please let this traffic through. So the querier is taking action and will managing the multicast group and send the data to the listeners. So, as I already mentioned, there's the MLD messages, or the querier needs a kind of messages to communicate with the listeners, and for that purposes there are two kind of messages. The first is a query message, which is used to announce to the listeners, hi, I'm the querier and please contact me, or some specific query message, we're coming to that later. On the other side, we have an MLD report, and in MLD version 1 we have also a done message. So the report is sent from the listener to the querier to tell, hi, I want to like to join this multicast group, please provide me the data. And if he's finished, he sends the MLD version, in MLD version 1, he sends a done message back to say, okay, I'm finished for now. In MLD version 2, this is summarized in the report as well. So he only sent a report message to tell, okay, I want to join, and he sent a report message again, I'm done with it. So just one message type for both purposes. So how does it look? Our querier set is an ICMP message, at least from type 130, and contains the information on which that in our network infrastructure some listeners can contact the routers to get multicast groups, and it is sent to the FF02:1. This is another multicast address which is used for the local link to address all nodes. So everybody in our local link will get this query message. Specific query message later on for additional communication are only sent to the multicast group they being queried. So if I'm joining a multicast group and there's some additional information for this group, the query is only sent in the group itself. On the other side, the listener is also an ICMP type 143. And in MLD version 2, you can announce all your multicast groups you want to join in one report. So as a listener, you just send one report and say, okay, I would like to listen to this, all of these groups back to our querier. And this is FF02:60, which is a multicast group for all MLD version 2 capable routers. So all MLD capable routers will get this, and the querier will handle and manage then the rest. So now we know basically how MLD is working. Let's get to some funky nodes we found as we did a little bit deeper understanding how MLD works. So the first funky node is state keeping on the router. He has to keep state on all multicast group every listener wants to join. And additionally, he has to keep state of, for every multicast group, which sources the listener want to get the data stream from. And every entry in our table is there's a timer, and if this timer exceeded, the entry will be deleted. So the timer is basically for getting clear the table, but it will every time renewed. Our listener called back and said, "Hey, stop! I'm listening, or I'm still listening to this." So next funky node, MLD, even it learns to manage the groups and which sources these multicast groups provided, it does not learn how and how many listeners there are in our network, or at least in this local link. So it has no clue how many listeners are connected to his. The next addition is that the querier election, which becomes the main querier if we have two or many routers in our local link, is based on the lowest IPv6 address. So this sounds fun. And in MLD version 1, some clients even not send their own reports if they already saw that another client sent the same report to the querier, which could be a good reason, but let's see. And funky node 3, we saw in one on the main RFC that every node has to accept every querier message on all addresses on the interface. So it's not, basically MLD is working over multicast, but we can communicate even one-to-one communication on the local link. And the RFC says, okay, this is for debugging purposes, but we will see as well. So are there any good news about MLD? Since it's very complex, we have to keep state on everything, so the router needs more memory space. But Up until this point, you don't need MLD. But needing and running are not the same. And the IPv6 clients, or the capable clients who are running IPv6, running MLD as well. At least all of we have tested. The only exception we found was OpenBSD, which is not enabled, or MLD enabled. And MLD is, from the RFC side, recommended, or at least every client should implement it and understand it. So more complex for our environment. So summarizing till now, complex, resource-intensive protocol we usually do not need in our environment. At least we have no multicasting. Some nice features like increasing state keeping for our infrastructure. You can become querier in at the local link very easily. Communication with the queriers or other clients on the one-to-one communication base. So not anybody seeing if we communicate with the querier. And you can force your network devices to go back to MLD version 1. And this is not just theory and on the paper. We take a little look in the wild and build our own lab environment. And this is what we brought with us. This is 2 routers. Behind one router we have a multicast source, which is providing a data stream. And on the other side we have on the switch some virtual guest host system and of course our attacker. And our tools we mainly used were Scapy, Chiron, Dizzy, the THC IPv6 toolkit, and Wireshark. Chiron is a tool, or more an IPv6 army knife from Antonius Atlasis. He developed this tool especially for the purpose to test IPv6 and IPv6 protocols. And Dizzy is a fuzzing suite from a co-worker of us, and you can use it as well for fuzzing IPv6. So we start testing, and the first scenario we did was, okay, let's just send a query out in the wild and see how our clients are responding. And the first we note is Windows, Ubuntu, Android, and FreeBSD responded very immediately after our query. So now we take a look at the RFC, and the RFC says the client must not respond immediately after a query. So all of them are doing not that well, at least from the RFC side. And the RFC says mention also that might be some problems if they respond immediately. And what you can see here is this is the time where just our router sent periodically in some time-based some queries, so not every time, just in 120 seconds. And after 50 seconds, we started to send an MLD version 1 query, or better not one, we sent 10 per second. So we sent statically MLD version 1 queries, and at the same time, the amount of reports replying back from our clients, in this scenario 4 clients, our traffic rise up. So, and it rise up 38 times more than before. And imagine you have an environment with not 4, with 100 or 500 clients, and there's a little router managing all these clients, and an attacker will start sending an MLD query periodically, which is not that hard. All the clients will come back to the router and report them statically every time, hey, I would like, or here I am, and so on. And this will be heavy load for the router. And as usual in the IPv6 world, Windows behave a little bit different and weird. And we saw in MLD version 2, there's a slight use of CPU power, but MLD version 1 use at least one core, got an amount of mostly 100% usage. We don't know what the core is doing or processing in behind, but he will do some magic. So at this point, I will hand it back to Jason, and he will guide you to the rest of our tests.
So, switching. Okay, so one thing worth mentioning in this scenario is that this was achieved, like every query triggered this kind of behavior. Like it wasn't that we were like trying to overload the network. It was just like we were sending periodical queries, and then the very same scenario, the very simple scenario which behaved in this way, started behaving in this sort of way. The same with this scenario, like once we started triggering interrupts on the Windows side via MLD version 1 queries, the system started becoming unresponsive, and we suppose, like we did a short analysis of why the protocol was behaving that way and what was causing the CPU consumption. And we guess it's the interrupts, like the interrupts, every time a packet comes and like the network card is not able to process all the packets going to a different multicast address. So the network card says the CPU, hey, I can't handle this, please kernel process this packet, like on software. And then that's where you get this behavior, like you get one core getting overloaded and so on. So it's a bit weird and uncomfortable, especially in virtualized environments, but it's not that a big deal. But if you look at the router side, what you get is like you jump from 0% packet loss to sometimes 10% packet loss, 20% packet loss, or 50 and sometimes 100% packet loss, just by increasing like the throughput you're using, like trying to overload the network with MLD version 1 queries, or in this case with MLD version 2 reports. Why this happens is because of this. As Rafael mentioned, we can, in an MLD version 2 report, like just stuff it with several MLD version IPv6 addresses, like just said, okay, dear router, I want to report that I'm listening to certain groups. Here you have this list of groups. And if we fill this multicast version, MLD version 2 reports with source addresses and tell the router that we're listening to a lot of addresses, then the router is going to start catching all of them. And what happens when the router cannot catch any more multicast sources anymore? So the router becomes unresponsive, packet loss starts happening. Like we also get a sporadic switching off of the Ethernet interfaces and so on. And as we can see here, we took, in this screenshot we go from 0% packet loss to 8% packet loss. In the test we're going to do here, we're going to get about 80% packet loss or 90% packet loss. It depends. There are some spikes and so on. And obviously the jitter is going to go high and go crazy. So what you should be asking yourselves is, this is a really complex protocol to manage a really simple task. Do we really need this in normal IPv6 deployments? You can mitigate this by putting a hard limit on the number of multicast groups which can be joined. That would not be recommended because a malicious user could anyway like fill those entries which were reserved, so to speak, and then no other clients would be able to join a particular multicast group because the router is going to say, no, there's no more space. So what the approach would be like limit the rate at which the router can process this kind of messages. That would be a more sensible approach. But anyway, you shouldn't have to go this way in order to manage to configure or manage something which is essential in IPv6 or an important part of IPv6. So what starts happening processes start failing, like multicast routing starts failing, the DHCPv6 server fails. That means you cannot lease any more IPv6 addresses. And at the end, you cannot even execute a command on the router. Your router is at this point effectively DOS'd. Some people have said that it is possible to achieve the same effect with ARP. In our tests, we only managed to trigger this kind of behavior with MLD and with really big MLD version 2 reports. So we think like the leap from IPv4 to IPv6 is not exactly positive in this sense. Like we are overloading the router in a way we shouldn't do or isn't needed. So let's have a look at what happens. Okay, that's good. So here we have like a normal serial cable to a router, to the first router, and then we're just going to start sending DZ packets. Like here I have my commands, and then we're going to start sending DZ packets to the router. DZ is just generating MLD version 2 reports, really big MLD version 2 reports, in order to try to overload the router and like fill the multicast cache, the MLD version. The MLD cache. So I'm just going to copy this. So there's that. So we start sending packets, and what we start seeing on the router is like there are a lot of groups which were joined, and the router tries like to keep up with them. However, as you see here, like the packet load starts going up. It's going up slowly because I had that command running like for a while. But now here you see that I'm not getting like any responses from the original device, like from the other side of the router, from the outer side of the router. I'm not getting any replies. So if we stop DZ, the router recovers, and then the packet loss starts going down again. So that's uncomfortable, of course. No network administrator wants to have that behavior in the network, especially because it becomes really hard to predict. Like there was a lot of discussion some months ago regarding the predictability of IPv6 networks and how you should manage them, and the fact that you should have or should not have big IPv6, like big Ethernet broadcast domains. And some people in some data centers were really having problems with MLD, causing their switches and their routers to behave weirdly, especially their switches. Like spanning tree protocol no longer working. And as you can see here, that's not just theory, like fear mongering, it can happen. It can overload the router and even the switch. So what does that happen? Like just useless defaults by, in our case, Cisco. Like why does the router need to learn 150,000 multicast entries? You are not likely to be using that. And anyway, if you're using multicast applications, you would be at most like using 10, 20, 100 multicast groups, not these many. So if you want to mitigate this, as we've mentioned, like you should use control plane policing, the rate at which the router processes this MLD version 2 reports. But there's not only like denial of service attacks against a router or the switch. but there are also crashes due to the malfunctioning of network card drivers. So we sadly can tell you which hypervisor crashes whenever you start like playing with MLD on your network. But it's an enterprise-grade solution. It's pretty used. I mean, like we find it on almost any assessment we do. And you just start sending big MLD version 2 reports, and at some point, like 30 seconds or 40 seconds into sending packets, the driver just crashes, and then you have a kernel panic, and then you get a beautiful screen of death. So like the equivalent of the screen of death in the platform. And what we see is, okay, multicast wasn't anyway a big deal in IPv4. So it was used, there were companies using it, there was research using multicast, there were people actively using it, but our infrastructure and our devices aren't kind of capable of going along with it that well. So this kind of behavior is to be expected, like drivers behaving weirdly, and your routers, I don't know, I think at this point I would like to advise you to test it, your Juniper, your Huawei, or whatever you're using to see out of the blue the spanning tree protocol stops working. So let's not forget the scenario. We have multicast source or backbone, which somehow delivers the multicast traffic to our listeners. And here is the malicious user, which is trying to somehow prevent the other clients to either get out, like via denial of service, doing a denial of service on the router, or just trying to prevent this listener to receive particular traffic. Like, let's say there's video conferencing for the management going, and this person wants to prevent this listener from receiving IPTV or video conferencing content. So that's also possible due to the rather naive approach of the MLD protocol, like the naive design. And especially, there are like funky things. Rafael already mentioned that you have this MLD version 1 suppression, like the fact that I can say, hey, I'm listening to this group, and if the network is in MLD version 1 mode, and anyone else listens to my report, then this client is likely to say, hey, someone already reported this group, so I'm not going to report it. The thing is, since you can at any point send an MLD report to the specific client, the router is not going to notice. Like, you can just put the link local address of a particular client in the IPv6 packet and send this report to that particular client, and then from the side of the client is going to say, okay, I've already seen this report, I'm not going to report it. Windows machines implement it, and in this case, the FreeBSD machine we tested with FreeBSD 10 did it as well. Like, at first, when we sent a query from our Kali machine, the FreeBSD machine replied, hey, I'm listening to these groups, but I'm also listening to this one. And then we said, okay, let's just try to suppress the reports for a particular group. We sent a multicast version, an MLD version 1 report for this particular group, and then what we get when we send the query is we get the same ones in the beginning, but we don't get the one in green here. So you can do that if that's what you want to do, like try to suppress reports from clients. But there's something even funnier, like in MLD version 2, when a particular client says, okay, I don't want to listen anymore to this multicast traffic, so please, router, if you want to not forward it anymore into the network, just do so. So the router is not dumb, and the router says, okay, I'm going to ask if there's anyone who's interested in this traffic still. So the router does that. What happened in our scenario is we weren't seeing this second query. Like, the Kali said, okay, we don't want to receive this group anymore, and the router was expected to send the other query, like the so-called last listener query, but it didn't send it. So we started wondering, and we found out that it was the switch blocking this kind of queries, not the router who wasn't sending them. So it's even easier, like, as an attacker or as a malicious user, in order to DOS or prevent this client from receiving a particular traffic, you don't have to like do anything complicated. You just say, hey, dear router, there's no interest in this particular group. And then the router says, okay, I'm going to try to see if that's true, sends the last listener query, and then the switch blocks it. So that's pretty dumb. And it's the easiest approach. Like if you have the iOS image we have installed here, it's 15.3, 15.4. So if that's the case, then you can just simply send an MLD version 2 report saying the network, the router, no interest, and the switch is just going to block the last listener query. If that's not the case, then you can just like become the querier, which is easy. You can just send an IPv6, an MLD version 2 query from a lower IPv6 address as the router. Then you can leave the group, like say, okay, I'm not the querier, and then you send the router, the other routers, an MLD version 2 report saying there's no interest in this group. And then you fake the last listener queries. You send 2 fake last listener queries, and then from the perspective from the other routers, they're going to say, okay, I'm not the querier, someone said there's no interest, and I've already seen the last listener queries. So I can delete this one. And then the traffic is not going to be forwarded anymore, whatever the traffic is for that particular multicast group. So yeah, in reality, the fact that the switch in our case blocks the last listener query makes it even easier for us. And then let's do a short demonstration. So just to give you like a feeling for how the setup looks like, because it's a bit like here we have 2 VLANs. We have VLAN 100, which is 2001 DB821, some address. And then we have VLAN 200, which is 2001 DB82. So my PC is connected to both VLANs, and in each VLAN we have a sender sending data, and we have a receiver receiving that data. Like in the same scenario I showed you with routing infrastructure and a sender and a receiver, we have that very same setup here. There's also multicast routing going on between both of the routers and so on. So what we're going to do is a really simple test. We're going to start listening to this group, and then on the other side we're going to start sending multicast data. So we see that like the data is multicasted and it reaches the router, the listener, in the VLAN 100, and it comes from the VLAN 200. So where are we sending the data? We're sending the data to the group FF08, FF08 : DB8. If we try that with a video stream, it's the same case. Like if we try to just open a video stream, it should work in the same way. Like we're retrieving data from the group FF08 : DB8, and that data comes from the sender on the other VLAN. So if we now go and do what I just mentioned, like we first become the querier. We first try to become the querier. We tell the network, So now we tell the network, hey network, I'm the querier, and then we go to the router. Let's go to the router and see who's the querier. So the router now says, okay, the querier is FE80 : A. So we are now the querier. And now we're going to tell the router, okay, there's no interest in this particular group anymore.
Show that the videos are still running.
Yeah. So here we see the video is still running, and then let's just say tell the router there's no interest in that group, and then let's just fake the 2 last listener queries, which we have here. So there goes one of them, and there's the second one. And at this point, we should have no longer a video transmission. So that's the funny thing about MLD. Like, you can do this really, really easily. Well, it's just the way protocol should work. So if you now go to the router and do show IPv6 MLD groups, you see that the router, from the perspective of the router, no one is listening to that particular group. So yeah, that's the one thing about MLD. Like, there are several variations you could do from these. Like, you don't have to first become the querier. You can do it using MLD version 1. You can do it using MLD version 2. Like, there's several combinations you could do. Like, here we're just showing you, because of the time we have available, like one particular way in which you could do it. The thing to keep in mind is, if you're using multicasting, IPv6 multicasting, and are relying on MLD in some way, then you should keep this in mind. Like, some people said IPv6 just works. No, it sadly isn't that way. So, but someone had to add something else to the mix, to an already complex protocol in an already complex stack. Someone had to add something else. So what people decided to add, like vendors and so on, was a particular implementation called MLD snooping. In our scenario, like when the router sees, the router serving the VLAN 100 sees the multicast traffic, Rafael already mentioned, like, the router doesn't know who specifically is listening to the multicast data. So the router just gives that to the switch, and the switch says, poop, it's going to everyone, to all of the clients on the local area network. So some people started wondering, hey, that's not that efficient. So what if the switch learns where there are listeners for a particular group? If you have already, like, understood the gist of MLD, you should already start thinking, hey, but that means we're also keeping state on the switch. So yeah, that's right. Cisco, for example, Cisco in this case devised an implementation called MLD snooping. So what MLD snooping enables is, this is the normal case because switches behave this way. If you send multicast traffic, the switch is just going to say, I'm going to send this to everyone. So if you have an MLD snooping enabled switch, the switch is going to say, okay, I know that there are listeners here and here, so I'm just going to forward multicast traffic to those two clients. The problem is that it requires the switch to also keep state. And then what happens is what happened in the same case. When you have MLD snooping enabled, you start getting high CPU consumption. In this case, you don't get packet loss, like like a percentage of packet loss, which is going to greatly impact your quality of service agreements or whatever, but it's going to not allow your network to perform in the way you are accustomed to. And it's certainly problematic in most settings. Like, so yeah, at this point, I guess you're going to be wondering, so is MLD really that useless? Like, do we really need MLD or don't we really need MLD? What's the real role here? So the thing is, you can not only do what we've shown you here, you also make it possible for attackers to, like, when you get into a host, you start thinking about pivoting, right? So you start thinking, okay, where I'm going next? And in IPv6, everyone says, okay, in IPv6, you have to scan the whole range or use weird DNS tricks in order to discover where the other hosts are, and so on. So with MLD, you don't have to do that. With MLD, if you're on the local link, what you can do is spoof a single query and just send it to the network, and all the clients which are in that very same local area network are going to reply, hey, I'm here. So that's a really peculiar, easy, and scary way to just like scan a network. Even if you disable ICMP replies, MLD is required from the RFC side to be running, so systems are going to still reply to MLD messages. They're not going to be blocked. even if they don't reply to ICMPv6 echo request messages, because MLD messages are based on ICMPv6, but there are no echo request or echo reply messages. They have a different type. So systems still answer to them. You can use Chiron's KP or the THCv6 toolkit to do this very basic reconnaissance using MLD version 2 queries or MLD version 1 queries. You can also use Nmap, but there's a plugin which is a bit buggy. We did some modifications in the plugin, and we're going to contact the person who wrote the plugin in order to see if they want to include the changes. But we just wanted to let you know that there are possibilities. If you need to do some IPv6 scanning in a local link, you can just do it in this way. Just send an MLD version 2 or MLD version 1 query, and the relevant nodes are going to reply. There's also an interesting fact. Some systems join different multicast groups. If you have a Windows system, you're going to join FF02::C or FF02::13. If you have a FreeBSD host, you're going to join two groups which are associated with an experimental feature from IPv6 called the node information query. Why that's the case by default, I don't know. Why FreeBSD joins this group, even if it's defined in experimental RFC, escapes me. But just so you know, it's something which is plausible. You can kind of infer from the groups which are joined by a particular host which kind of host it is. It's not reliable, of course not. I could join this group in a Windows machine, but it's another piece of information. So, as I already said, is MLD really that useless? It only serves malicious users and attackers to do pivoting and to the DOS my router and my switch? Well, of course you can use MLD when you're running multicast applications. If you have here your backbone or your enterprise routers, and you have your multicast source, you're doing video conferencing in another domain, and you need inter-domain multicasting, then of course you're going to need MLD, because the listeners have no way to tell the router, hey router, please forward this kind of traffic when you see it. But how many of you have deployed multicast in your networks? Could you raise your hands? I see one hand, and that's a bit sad because it's interesting. It's an interesting technology, and there are a lot of protocols and things we could improve using multicast, but it's just the way it is. It's not always the way we would like it to be, and multicast is not that widely deployed anyway. So we see that the core use case of MLD is something which is not that widely deployed. Where can it also be used? It can be used for improving, for getting rid of broadcasting. That was the initial thought. Okay, we're going to replace broadcasting, but we have to replace it with something else. What if we replace it with multicasting? So now I want to contact Rafael, and I have Rafael's IP address, and I want to ask Rafael, if it was ARP, I would contact Rafael and tell him, hey, anyone does have this IP address? And then Rafael would say, yes, I do have this IP address. So we don't have this broadcast mechanism anymore in IPv6. So what the IETF and the folks working on the RFCs developed was okay, so whenever a host goes up, this host tries to give itself an IP address if it's using stateless auto-configuration. So this host gives itself an IPv6 address and joins a group, must join a group, a multicast group. Whenever someone in the network tries to reach this host, the one who tries to reach it is going to generate the multicast group using the IPv6 address and send the message to that particular multicast group. Whoever is on that group is going to reply back. So these groups are usually only populated with one host, because I get an IP address, I join this multicast group, and I wait till anyone wants to ask me anything, who neighbor solicitation message, who has this IP address, and then I reply, hey, I'm here. So the problem is, apparently it was problematic for Cisco to implement, to manage neighbor discovery messages in a different way when MLD snooping was enabled in the switch. So at some point there was a bug, like from 2012 or 2013, and there was someone saying, okay, MLD snooping is breaking neighbor discovery. Neighbor discovery is not working anymore because I enabled MLD snooping. And the problem was that MLD snooping was saying, okay, there's no one listening to this particular multicast groups because the hosts are not required to send reports for multicast groups associated with the neighbor discovery protocol. So at some point, Cisco just started managing it differently. In our case, like the Cisco switch just says, even if MLD snooping is enabled, this is neighbor discovery traffic. We're not going to play with it and just broadcast it. So it should behave this way. We should, like, if we have a switch with MLD snooping enabled and this one is asking, hey, who has this IP address? This one is in that multicast group. This one only should reply or should get the message and reply, and this one is going to have the information it was requesting. However, the scenario is totally different. You're not winning anything in terms of performance or getting away from broadcasting by enabling MLD snooping or by using MLD. We must always think that MLD is like the way hosts join groups, and since this multicast thing we tried to develop in order to get away from broadcast functions on top of groups, we use MLD for that. So it's really weird, I know, but it's the way it is. Like, we're using a underused feature for a really popular feature or protocol, which is the neighbor discovery one. So yeah, and then we have this funky kind of writing style on the RFCs where you have MLD report message is required in order to inform MLD snooping switches. But MLD snooping is not a standard. So why is MLD snooping being considered in the RFCs? Important RFCs like the neighbor discovery one. Once again, so much for predictability. So this is the scenario, like the green line is using normal multicast traffic. The switch behaves in the way you would expect. If you have MLD snooping enabled, the sender sends some multicast data and only one system gets it, or the systems which joined the multicast group. However, when you use neighbor solicitation messages, for example, everyone gets them. So what's the point of MLD snooping? What's the point of MLD on the local link, like not on the multicast scenario, which only one person in the audience was using, but in the general scenario, which everyone has? There's more or less no point of it. At least from our perspective, there's no need for MLD on the local link. And as you see here, like we sent neighbor solicitation messages and we got them. We sent it through one and we received it through the other two. In the case of normal multicast data, it was just sent to the other one, like to the one on the slide. There is a draft on the ITF, an expired draft. It didn't go nowhere, where Pashby and others were saying like, okay, MLD is too complex. It's not worth it. It's not worth it to do MLD snooping for neighbor discovery associated messages. Let's just do it another way. Like, let's just leave neighbor discovery alone. And apparently this is what happened in the case of Cisco switches. We're not sure if that's the case. We see that behavior, but the decision which Cisco made, it's not something we are like aware of. But it's useful to know that, because if you look at the documentation and you look at any manual and any configuration guides, it's always the same. MLD snooping is great for your network. MLD snooping is going to optimize multicast traffic, and then you go to some books and you read, okay, neighbor discovery is multicast traffic. It uses multicast in some cases. And then you make the connection, okay, so I'm going to use MLD snooping in order to optimize or to tune my network, and then you get this kind of behavior where you don't get anything from MLD snooping. So what have we learned? Like, the thing is, we've learned that we have to somehow manage MLD until we get over it, or either we go back to ARP-like behavior where we broadcast, or we start using another protocol, or we improve MLD. simplify MLD would be a better word instead of improving it. It is already complex enough. Stay away from MLD snooping. You don't need it. You likely don't need it. I'm not saying no one needs MLD snooping. It's likely that in your environment you're not going to need MLD snooping. And if you think you need it, please have a look at the documentation, have a look through the slides, do some tests on your environment, because as we saw, it's going to have an impact on your infrastructure. If someone, if because of a configuration problem, someone starts sending MLD messages, or an actual malicious user starts abusing the protocol. And try to statically join groups. Like, don't deploy full-blown protocol-independent multicasting when you're just like using 1 or 2 groups for video conferencing and broadcasting content from an IPv6 camera and so on. A couple of points for the folks from the ITA, in case there are any of them here, or like any of them have a look at the video. Routers should not accept queries like going to these kinds of addresses or going to unicast addresses. This was the basis on which we managed to talk on a one-to-one basis to the routers and to the clients. So in a protocol which is multicasting, like multicast oriented, where you're talking to everyone like, hey clients, tell me what are you listening to, you shouldn't be allowed to like ask some client, what are you listening to? Which is what we did by becoming the querier, only telling the querier that we were the querier, and then only sending like the last listener query again to the router and not to the other clients. So that's something which should be taken care of in our opinion, especially since it's for debugging purposes. Yeah, the same goes for nodes. Like MLD messages shouldn't be accepted under unicast addresses. It makes no sense. Like it makes no sense at all for MLD. And then like the query election mechanism should either be made more complex, like more robust, or either be like just made simpler. Like you have to define on your devices who is going to be the querier, period. Like not some simple middle ground where you get to just like spoof one query and just become the querier and start playing around. Why it matters? We think it matters because people are starting to talk a lot about IPv6, and we think it's good. We do a lot of IPv6 work at the company, and we are all for IPv6, but some people are starting to talk about IPv6 in the wrong way. Like they're starting to talk about it like everything gets an IPv6 address, everything gets networking capabilities. And if you're going to have such a network, such a complex environment where everything gets an IPv6 address and everything has networking capabilities, such protocols are not likely to scale. So we should definitely have a look at them, like the community itself should have a look at them, not only MLD, like MLD is only for the local link and perhaps from the attacker's perspective, a rather boring protocol. But there are really interesting like features and things which are hiding behind the label multicast, and it's something definitely worth looking at. There are already IPv6 cameras which you can just like configure, and they start like using multicast groups in order to share the information with the other clients which are listening to them. So it would be interesting to test them and see how they behave in the scenarios we just described. Like just start playing around with the groups, trying to leave them, trying to rejoin them, and so on. And appliances are getting cheaper, and everyone is, okay, let's build it cheap. So these kind of protocols and these devices can be built cheap when you have to keep state on routers, on switches, and in order to be able to sensibly deploy a multicast environment. So that's more or less what the talk was about. Like in order to show you, you are running MLD in your network. You are running for sure MLD on your network if you have IPv6. If you have a rather more modern operating system, the RFC requires any modern, like any new devices which come to the market to implement IPv6. Like you have to have, if you're going to default to IPv4, you have to have IPv4 and IPv6 capabilities. So you rather have already IPv6 capabilities in your devices, you are running MLD, although you don't know it and although it's not useful for your case. It's a complex protocol, can have an impact in your infrastructure, and if multicast is the future and if everyone is looking towards multicast and IPv6 as the future, we as a whole and as a community should be like having a closer look at it as a whole. And yeah, like of course, like the folks at the ITF should have a look at it and reconsider it. Like there are a lot of historical things in the protocol inside, like which were done that way at that point in time, but no longer apply. And the whole, like these whole problems we've been talking about also apply to wireless links, and they get worse. Like multicast on wireless is a problem. So not from a security point, but from like a power consumption point and efficiency point. So multicast on IPv6 is definitely something which must be looked at. And without further ado, like that's all from our side. Thank you for listening, and I don't know if there are any questions or like, yeah, let us know what you think, like what multicast should be like, or what questions you have regarding MLD or what we tested, or yeah. So that's all. Thank you.